Welcome back, Virtual Algebra 2. In section 10.4, there's kind of a basket of different things we're going to learn about. But kind of the focus is going to be on the difference between and or in probability. And there's a little other trick thrown in there as well. And the section is titled Using Addition in Probability, and that's a pretty good title. Alright, so let's look at a situation like this. We're going to flip a coin, and the coin can either come up heads or tails, because it has two sides, right? And then we're going to roll a die. You know, that six-sided square thing. Your book calls it a number cube. You know, like they use in casinos. And it can come out 1, 2, 3, 4, 5, or 6. So this is a pretty simple situation, and I've listed here all 12 possibilities. You can get a head on the coin and then a 1 on the die, or a tail on the coin and then a 1 on the die, a head and a 2, a tail and a 2, a head and a 3, a tail and a 3, etc. And there's 12 possibilities. And that makes sense from the point of view of the fundamental counting principle, right? Remember the fundamental counting principle? The number of possible outcomes in a compound event is equal to the number of outcomes in the first times the number of outcomes in the second. Well, the heads and tails, that's 2 possible outcomes. And the 1 through 6, that's 6 possible outcomes. So 2 times 6 is 12. Okay, so we got them all. And so what's the probability of getting a head on the coin and getting a 4 on the number cube? Well, there's only one way to do that. And so there's 1 out of 12 possible. And so the probability of head and 4 is 1 out of 12. What about heads or 4? With an or, either one will do. Getting a head on the getting a head on the coin and a 6, that satisfies heads or 4. Getting a head on the coin and a 4, well, that happens to satisfy both, so it satisfies the or. And getting a tail on the coin, but getting a 4 on the die, that will satisfy the or as well. So an or is not very picky. It tends to be relatively easy to satisfy an or. And you can see that here, when you count up all the possibilities, there are 7 ways to make this happen, and there are 12 total possible outcomes, so the probability of heads or 4 is 7 out of 12. And that's much larger than the probability of the and. An and tends to be really picky and hard to satisfy. We have to get heads on the coin and a 4 on the die. That's very picky, that's difficult. And the probability is accordingly very small, 1 out of 12. Now this situation is relatively simple, but when they get more complicated, it's going to pay off if we learn a sort of a different way of looking at this. So let's look at the and case first. The probability of heads and 4 turns out to be the probability of getting a head times the probability of getting a 4, right? The probability of getting heads on the coin, well, that's just 1 out of 2, or 1/2. And the probability of getting a 4 on the die, that's 1 in 6. 1/2 times 1/6 is 1/12. And tends to work that way. It tends to be a multiplication of probabilities. And when you multiply a probability, you usually get a smaller number, because a probability is a number between 0 and 1. All probabilities have to be between 0 and 1, because either it won't happen, or it will happen, or it's something in between. So when you multiply together two numbers that are between 0 and 1, you get a smaller number. Alright, that's easy. Now let's look at the or. Or tends to be, instead of multiplication, tends to be addition. This is really complicated, but hold on, we'll get through it. The probability of getting head or 4 has to be the probability of getting heads plus the probability of getting 4. Now you'd think you'd just stop there, right? But we have to subtract away the probability of getting head and 4. What? Why do we have to do that? I think it helps if you look at this diagram on the right. In the black, I've put a square around all the possibilities that include a head. And in the blue, I've put another square around all the possibilities that include getting a 4. And you can see that if we count up the 6 possibilities with heads and the 2 possibilities with 4s, we get 8. But you can see that we've overcounted because we've counted the one that's a head and a 4 twice. And so to fix that, we have to subtract away that one possibility that's heads and 4. And then we get the proper number of 7 possibilities out of 12. and that's the probability for this heads or form. Okay? Now this is a situation in which it is possible to have both of the pieces at the same time. It's possible to get a head on the coin and a 4 on the die. It's what's called an inclusive situation, where it is possible to do both. In general, though, something that's really important to take away from this is that when we add two numbers that are probabilities, that is between 0 and 1, we get a larger number, right? The probability of just getting heads was 6 out of 12. Just getting 4 was 2 out of 12. And even though we did have to do this weird subtraction, when we added them, we got a bigger number, 7 out of 12. And that goes along with the fact that an OR tends to be easier to get. It has a higher probability, and an AND tends to be harder to get. It has a lower probability. So once again, I'd just really like to emphasize the connection between adding and OR and larger probabilities, multiplying and smaller probabilities. Well, what happens if the events aren't inclusive? Really quickly, a simple example, if I just roll a number cube, or a die, what's the chance that I get a 4 or a 1? Well, I can't get a 4 and a 1. It's not possible on one roll. So I don't have to worry about this subtraction. I've added it here just to show you that it doesn't make any difference. The chances of getting a 4 or a 1 are going to be the chances of getting a 4 plus the chances of getting a 1 minus the chances of getting a 4 and a 1. Well, that's 0, obviously. So it's just 1/6 plus 1/6, or 2/6, or 1/3. All right? Here's what the formulas look like in general. The top two are in your book. The probability of A or B, when A and B are some events that are supposed to happen, like getting a 4 or getting a heads. The probability of A or B is just the sum of the two, the probability of A plus the probability of B, if the events are what we call mutually exclusive, meaning they can't both happen at the same time. If they're inclusive, like in our first example, then the chances of getting an A or B are the same, but we have to subtract away that chance of getting both. And we saw that. And then what's not in your book, but what we also just looked at with the 4 and the heads, is the chances of getting A and B. And that's just the product of A times B. The top two we're using addition and the bottom one multiplication. It's going to turn out later that we're going to learn that that is not always true, but for now it is. It's true for what are called independent events, which is what we're dealing with so far. All right, there are a few examples in your book that work off of this table. This table is showing us the results of a survey of men and women who said that they either favored or opposed or had no opinion about a change in policy. Okay, so for example, 25 women opposed the change, 20 men had no opinion, and then there are totals on the rightmost column and on the bottom row. So stare at this table for a minute and see if you understand what it's saying. In the first example, we're asked to find the probability that a person selected at random would either oppose or have no opinion about the change. Okay? This is an OR, so are we going to use multiplication or division? Multiplication or addition? Right, addition, because it's an OR. Now, are these mutually exclusive or are they inclusive events, opposing and having no opinion? Well, logically, they must be mutually exclusive. I can't both oppose it and not care. So they're exclusive. And so I can use the very simple version. I just add the probability that they oppose it to the probability that they have no opinion. Okay, we weren't told anything about men or women, and so the probability that they oppose it, well, that's the total number of people that oppose it, 37, divided by the total number of people surveyed, 100. And then the probability that they have no opinion is the number of people that had no opinion, 36, divided by the total number of people, 37. So I add, 100. So I add 36 over 100 and 37 over 100, and I get 73 over 100, or 73%. So the chance that a person selected at random will either oppose or have no opinion is 73%. And that's example 1.